The gravitational wave can come from a burst in the universe. Gravitational waves were predicted already by Einstein, but they were not detected directly up to now. They should exist, but no one has measured it. So there is now a big run on measuring a gravitational wave. But suppose now that you want to measure the effect of a gravitational wave hitting an object on Earth. Then you have, with a dimension of 10 minus, say 1 meter, you have to measure displacements of the order of 10 minus 20 meters. So that is 10 decades more than the atomic scale. We dreamed about a sphere of 3 meters. Well, no problem, you think. But this sphere is always in motion a little bit. The surface is not still standing, and the Brownian motion is much and much larger. The resolution we give with epsilon. Epsilon is a constant, about 8, K, the constant of Boltzmann, temperature, an inductance, and a resistor. These are device properties. We can say here we have the squid. We have here some parameters that we can optimize. You could maybe say, oh, take L is 0 of the squid. Fine, you have epsilon as 0, but you cannot measure anything. So you will never be able to detect something. So the difficulty is already have a good practical squid and get here a resolution which is in the order of h bar. Optimization of the device on this side is one topic, but here you see a very important parameter, the temperature. The epsilon is directly proportional with the temperature. So when you go from 4.2 Kelvin down to 0.1 Kelvin, say 100 millikelvin, you have already gained a factor of 40. So what you have to do is to cool down. You have to cool down this sphere to about 10 to 20 millikelvin. Antenna is spherical. It looks to all directions with the same intensity. 6 sensors you have there to measure this very small displacements. Spring system connected to it, and there this 10 minus 20 meters is already on this plate 10 minus 17 centimeters. Then comes here the superconducting part, coils, and here you have the squids. We have here the very sensitive detectors for flux. A very small displacement of the plate here, just in front of this green coil, give current changes here in the first squid and in the second squid. Finally, this first squid has to be made extremely sensitive. When you want to read it out with electronics, you will not see enough. The electronics is too noisy. It is one like this, a loop with some superconducting, say, Josephson junction elements in it. You see here some fins connected to it, and this is needed to really cool down such a device to the 20 millikelvin. It's a very compact two-stage squid, second stage of it, and then you come at a level that you can connect it to room temperature electronics. Are we close to measure a gravitational wave? Well, lots of research have to be done. We have to improve the antenna. We have to improve the squid readout system. Lots of work.
Der Urknall. Er muss ein Echo haben. Davon geht die Physik seit Albert Einstein aus. Er hatte in seiner allgemeinen Relativitätstheorie sogenannte Gravitationswellen vorhergesagt. Seitdem, seit fast 100 Jahren, sucht die Wissenschaft nach einem direkten Nachweis dieser geheimnisvollen Wellen. Bisher ohne Erfolg. Nun will die ESA eine neue satellitengestützte Technik erproben, um im Weltall Gravitationswellen zu finden. Die Wissenschaftler haben große Erwartungen.
LISA Pathfinder ist sehr wichtig für die Astrophysiker, weil wir damit ein neues Fenster ins Universum öffnen können. Ein Fenster zu den Gravitationswellen. Sie erlauben uns zurückzublicken zu den Anfängen unseres Universums, zur Entstehung von Sternen und Galaxien. Erlaubt uns, supermassive schwarze Löcher zu untersuchen. Wir können die Gravitation des Universums messen.
Die Theorie besagt, Gravitationswellen verkürzen und verlängern kurzzeitig die Abstände zwischen Objekten. Dabei geht es um Bruchteile eines Millionstel Millimeters. Ein Laser an Bord des Satelliten soll solche minimalen Veränderungen messen. Und zwar mit diesen zwei knapp 5 cm großen Würfeln. Sie sind auch an Bord und schweben in einem Vakuum. Verändert sich ihr Abstand zueinander, sollte sich das nachweisen lassen. Der Satellit ist eine Art Probelauf, bei dem vor allem Techniken und Messgeräte für spätere, größere Missionen getestet werden sollen. Noch befindet er sich im ESA-Testzentrum in Ottobrunn bei München. Ende November soll es dann für LISA Pathfinder vom Weltraumbahnhof Kourou aus in Richtung All gehen.